Welcome to SARK Tutorials, Learning Made Simple and Fun. In this first video of our kinematics series, titled Introduction to Kinematics, we will explore some fundamental terms and key concepts related to the study of motion. Motion is a core aspect of the universe. Understanding it enables us to describe and analyze the dynamic behavior of objects around us. Kinematics. Kinematics is the branch of mechanics that deals with the study of motion of objects without considering the forces responsible for that motion. It describes motion using parameters such as displacement, velocity, and acceleration. A solid grasp of kinematics serves as the foundation for studying more advanced topics in mechanics and physics. In this video, we will discuss the following key concepts in kinematics: object and observer, point object, rest and motion, frame of reference, motion in 1, 2, and 3 dimensions, scalars and vectors, distance and displacement, speed and velocity, acceleration, uniform and non-uniform motion. By the end of this video, you will gain a clear understanding of these foundational concepts, which are crucial for your further studies in physics. Object and observer. In the context of motion and observation, the terms observer and object are fundamental to understanding how motion is perceived and analyzed. These roles define the entities involved in any observation of motion. An observer is an individual who observes or pays attention to the motion of something else in its surroundings. For example, a car, bus, airplane, other person, or any other object. The observer perceives, records, or analyzes the motion of the object from his frame of reference. An object is anything whose motion is being observed. The object moves relative to the observer, and its position, velocity, or acceleration can be described based on the observer's frame of reference. Concept of a point object: every real object, no matter how small, possesses a definite shape and size and is referred to as an extended object. However, when analyzing motion, the treatment of an object can vary depending on the scale of the situation. Let's compare the size of the bus or car compared to the distance traveled by them. Short distance, for example 50 meters, the size of the bus or car is comparable to the distance covered. Their dimensions cannot be ignored and must be considered for accurate analysis. Moderate distance, that is 500 meters, although the distance is greater, the size of the object still has a noticeable impact and cannot yet be neglected. Large distance, that is more than or equal to 5,000 meters or 5 kilometers, the distance covered is significantly larger than the object's dimension. In this case, the size becomes negligible compared to the distance covered, and the object can be treated as a point object. A point object refers to an idealized object that has mass but no size, shape, or dimension. It is treated as a single point in space. This simplification is particularly useful in kinematics, where the focus is on the motion of the object, its position, velocity, and acceleration, rather than its shape or size. Rest and motion. In our daily lives, we observe various objects around us, such as trees, buildings, cars, buses, birds, and airplanes. These objects can be classified based on whether or not they change their position over time. Rest. Objects that do not change their position with respect to their surroundings over time are said to be at rest, such as buildings, trees, electric poles, and other stationary objects in the environment. Motion. Objects that change their position with respect to their surroundings over time are said to be in motion. Example includes car, bus, airplane, birds, and people moving from one place to another. Rest and motion are relative terms. The concepts of rest and motion are relative, as an object may be at rest with respect to one observer, while simultaneously being in motion relative to another. For example, a person sitting in a moving bus is at rest relative to their fellow passengers, but at the same time he is in motion relative to an observer outside the bus. In another example, a person sitting in a chair at home in his room is at rest relative to their surroundings in the room. However, relative to the Earth's axis of rotation, He is moving at a speed of approximately 1,675 kilometers per hour. And relative to the center of the sun, he is moving at a much faster speed of approximately 107,500 kilometers per hour. An object's state of rest or motion is not absolute. It depends on the chosen frame of reference. Thus, rest and motion are inherently relative terms, emphasizing the importance of specifying the observer's point of view in any analysis. Frame of reference. Let's consider a car is moving from initial position to the final position as shown in diagram in the presence of an observer who is observing the motion. To specify the position of an object, we need a reference point, denoted as O, also known as the origin, which may be the initial position of the car or position of observer. From this reference point, we establish a coordinate system and time measurement. A straight line drawn from the origin in the initial direction of motion of the object is called the x-axis. A line perpendicular to the x-axis is called the y-axis. A line perpendicular to the xy plane passing through the origin is called the z-axis. Additionally, the observer has a clock to measure time. This coordinate system x, y, z axis along with a clock constitutes a frame of reference. Hence, we can define a frame of reference as a system of coordinate axes attached to an observer along with a clock that is used to describe the position, displacement, velocity, and acceleration of a moving object. Motion in 1, 2, and 3 dimensions. Motion is categorized based on how many coordinates out of x, y, and z of an object's position changes over time. One-dimensional motion. Motion is said to be one-dimensional if only one coordinate changes with time. Examples includes a car or train moving along a straight road or track, an object thrown vertically upward or downward. As the object in this type of motion moves along a straight line, so it is also known as rectilinear motion or linear motion. Two-dimensional motion. Motion is said to be two-dimensional if two coordinates change with time. The object's motion is confined to a plane such as the xy plane, yz plane, or xz plane. Examples includes a car or person moving along a path in xy plane, a lizard or ant moving on the walls of a room. Circular motion, projectile motion. Motion in a plane that is not a straight line is called curvilinear motion. Three-dimensional motion. Motion is said to be three-dimensional if all three coordinates, that is x, y, and z, changes with time. The object moves freely in space. Examples includes birds flying in the sky, an airplane in motion, a kite flying on a windy day, and random motion of gas molecules. Scalars and vectors. Understanding the concepts of scalars and vectors is fundamental in studying the motion of objects. All measurable physical quantities can be divided into two classes, namely scalar quantities and vector quantities. Scalars. These quantities are represented by the symbol phi. The physical quantities that are completely described by a magnitude that is numerical value alone are called scalars. They do not involve direction. Examples of scalar quantities are mass. Represented by symbol m, value of mass can be written as 1 kilogram, 50 kilogram, 300 gram. Time, represented by symbol small t. Values of time can be written as 1 hour, 30 minutes, 40 seconds, 6 o'clock. Temperature, represented by symbol capital T or K. Values of temperature can be written as 23 degrees Celsius or 98.7 degree Fahrenheit. Length, represented by symbol L, its values can be written as 5 meter or 10 kilometers. Distance, represented by symbol S or delta L. Speed, represented by symbol phi. Any type of energy, like kinetic energy, potential energy, work. Scalars can be either positive or negative. While many scalars are always positive, like mass, distance, or speed, and some can be negative. Here are a few examples. Temperature can be positive above zero or negative below zero in Celsius or Fahrenheit scales. Work done can be positive if force and displacement are in the same direction, or negative if they are in opposite directions, and so on. Vectors. In writing, a vector can be represented by a single letter with arrowhead above it, that is vector A. The physical quantities which have both a magnitude and a direction are called vectors. Graphically, a vector is represented by an arrowed line OA. The length of the line on a suitable scale represents the magnitude of the vector, written as modulus of vector A or simply as A. The arrowhead indicates the direction. The starting point of the line is called the tail or origin of the vector. The endpoint or arrowhead is called the tip or head of the vector. Examples of vector quantities in motion are displacement, represented by vector delta r, velocity, represented by vector v, acceleration, represented by vector a, momentum, represented by vector p, force, represented by vector f. We will explore more about vectors in the upcoming video. Distance and displacement. Imagine a scenario where you travel from your home, point A, to an art gallery, point D, along the route ABCD, as shown in the diagram. You begin at point A and move straight to point B, covering a distance of 8 kilometers. Upon reaching point B, you turn left and travel 3 kilometers to arrive at point C. Finally, you make another left turn and continue for 4 kilometers until you reach your destination, point D. Distance, represented by S or delta L. The length of actual path traveled by an object while going from initial to final position is called distance. It doesn't matter which way you go, it just adds up how far you moved. The distance traveled, that is delta L or S by U, is sum over B, C and CD, that is 8 plus 3 plus 4, which equals to 15 kilometers. The length of the actual path traveled by a vehicle is given by its odometer. Distance is a scalar quantity. Distance can never be zero or negative. Displacement, represented by vector delta r. The displacement is the vector drawn from initial position to the final position, with its magnitude is equal to the length of straight line connecting these 2 points and directed from initial to final position. Magnitude of displacement, written as modulus of vector delta r, corresponds to the straight line distance between the initial and final positions. To determine the length of straight liner D, a perpendicular is dropped from point D to the initial direction of motion, that is liner B, meeting it at point N. Applying the Pythagorean theorem in the right-angled triangle A and D, the magnitude of displacement is given by the hypotenuse equal to square root of sum of squares of perpendicular and base, that is square root of sum of squares of 3 and 4 equal to 5 kilometers. The direction of displacement is expressed in terms of the angle theta between liner D and the initial direction of motion. Using the tangent function, we can write tangent theta equal to ratio of perpendicular to base, which in this case equals to 0.75. Displacement is a vector quantity. Displacement can be positive, 0 or negative depending on the direction of motion. By analyzing the distance traveled and the magnitude of displacement at various points during the motion, we can compare the two measurements as follows. The distance from point A to point B is 8 kilometers and displacement is also 8 kilometers. The distance from point A to C is sum of 8 and 3, totaling 11 kilometers, while the displacement is calculated as the square root of sum of squares of 8 and 3. Which equals to 8.54 kilometers. The distance from point A to point D is the sum of 8, 3 and 4, resulting in 15 kilometers, whereas the displacement is the square root of sum of squares of 4 and 3, which equals 5 kilometers. From this analysis, we can conclude that the distance traveled is always greater than or equal to the magnitude of displacement. Unit. Distance and displacement are measured in meters, centimeters or kilometers, depending on the scale of measurement. Dimension. The dimensional formula for both distance and displacement is m raised to power 0, l raised to power 1 and t raised to power 0, indicating that they have dimensions of length only, with no dependence on mass or time. Speed and velocity. Imagine the same scenario again where you travel from your home, point A, to an art gallery, point D, along the route ABCD, as shown in the diagram, but this time with an observer tracking your position and time. You depart from your home, point A, at approximately 8 a.m. and heading straight to point B, covering a distance of 8 kilometers. From there, you take a left turn and travel 3 kilometers to reach point C. Finally, you make another left turn and continue for 4 kilometers, arriving at your destination, the art gallery, point D, at around 8:30 a.m., completing the trip in 30 minutes. Therefore, as discussed earlier, we can write distance covered by you, that is delta L, is equal to 15 kilometers. Magnitude of displacement, that is modulus of vector, delta R, is equal to 5 kilometers. And time taken to cover this distance or displacement is equal to 30 minutes or half an hour. Speed, represented by a symbol v. Speed measures how fast an object is moving without any reference to the direction. Speed is a scalar quantity because it only has magnitude and no direction. Speed is defined as the total distance traveled divided by the time interval. That is v equal to distance traveled divided by the time taken, or delta L divided by delta t. Speed can be 0 or positive but never be negative. In the example discussed above, the speed of object can be written as speed equal to delta L divided by delta t, which is equal to 15 kilometers divided by 0.5 hours, that is 30 kilometer per hour. Velocity, represented by symbol vector v. Velocity measures how fast an object is moving in a particular direction. Velocity is a vector quantity with its magnitude given by the ratio of displacement to the time interval. It is always directed along the displacement. That is, velocity is equal to the ratio of displacement to time interval, or can be written as vector delta r divided by delta t. The velocity of an object can be positive, 0 or negative. In the example discussed above, the magnitude of velocity is equal to ratio of magnitude of displacement to time interval, which is equal to 5 kilometers divided by 0.5 hour, that is 10 kilometers per hour, and is directed along the direction of displacement. Since distance is always greater than or equal to the magnitude of displacement, it follows that speed is always greater than or equal to the magnitude of velocity. Unit. Speed and velocity are measured in meters per second in the SI system or kilometers per hour for practical use, depending on the scale of measurement. Dimension. The dimensional formula for both speed and velocity is m raised to power 0, L raised to power 1, and t raised to power minus 1. This shows that speed and velocity are quantities that describe motion in terms of distance and time without any influence from mass. Acceleration, represented by vector A. Now let's observe the same motion again. We notice that the car starts from rest, gradually increases its velocity, then moves some distance at a constant velocity. As it approaches a turn, it slows down before increasing its velocity again, repeating this process until it reaches its destination. This indicates that both the magnitude and direction of the car's velocity change throughout its motion. The quantity that measures this change in velocity, whether in magnitude, direction, or both, is known as acceleration. Acceleration is a vector quantity whose magnitude is given by the ratio of change in velocity to the time taken for that change. It is always directed in the direction of the change in velocity. Mathematically, we can write acceleration is equal to ratio of change in velocity to time taken. The acceleration of an object can be positive, 0, or negative. Acceleration is positive if the velocity is increasing and is negative if the velocity is decreasing. The negative acceleration is also called retardation or deceleration. Unit. Acceleration is measured in meters per second squared in the SI system or centimeters per second squared, depending on the scale of measurement. Dimension. The dimensional formula for acceleration is m raised to power 0, L raised to power 1, and t raised to power minus 2. This shows that acceleration is the quantity that describes motion in terms of distance and time, without being influenced by mass. Classification of motion. An object can be in one of two states: at rest, that is, its velocity is equal to 0, or in motion, that is, its velocity is not 0. When at rest, the object does not change its position with respect to its surroundings over time, and when in motion, the object changes its position with respect to its surroundings over time. If an object is in motion, it can be classified into two types. Uniform motion, that is, its velocity is constant, means its acceleration is zero, or non-uniform motion, that is, its velocity is not constant, means its acceleration is not zero. An object is said to be in uniform motion if it covers equal displacements in equal intervals of time, no matter how small the time intervals are, and the direction remains unchanged throughout the motion. Mathematically, velocity equal to ratio of displacement to time taken is constant throughout its motion. This type of motion occurs when an object moves along a straight line in one direction, that is, one-dimensional motion. In non-uniform motion, an object moves with a variable velocity, meaning its speed, direction, or both change with time. For example, consider traveling in a car. You start from rest, gain speed over time, and may travel at a constant velocity for a while, then slow down to take turns. The process repeats until you reach your destination. Since the velocity changes at different instances, this motion is an example of non-uniform motion. Variable velocity. An object has variable velocity if either its magnitude, its direction, or both change with time. In the case of non-uniform motion, we introduce two important velocity concepts: average velocity and instantaneous velocity. The average velocity is the uniform velocity with which an object would cover the same displacement in a given time interval as it does with its actual variable velocity. Mathematically, we can write the above expression as, for example, in the motion discussed earlier, the magnitude of average velocity is 10 kilometers per hour. While average velocity gives an idea of how fast an object has moved over a time interval, it does not describe the speed at each instant. The instantaneous velocity at time t is the limit of the average velocity as the time interval approaches zero. The magnitude of instantaneous velocity is equal to the instantaneous speed at that moment. The speedometer of a vehicle measures the instantaneous speed of the vehicle. In non-uniform motion, an object's velocity varies over time, indicating that the motion is accelerated, that is, acceleration is non-zero. Acceleration can be either constant or changing, allowing us to further categorize the motion as uniformly accelerated motion, where acceleration is constant, and non-uniformly accelerated motion, where acceleration is not constant. An object moves with uniform acceleration if the change in velocity per unit time is constant. Such motion is called uniformly accelerated motion. In non-uniform acceleration, the velocity changes by unequal amounts in equal intervals of time, meaning acceleration varies. For non-uniformly accelerated motion, we define two important acceleration concepts: average acceleration and instantaneous acceleration. When an object moves with variable acceleration, its average acceleration over a given motion is defined as the ratio of the total change in velocity to the total time taken for that change. Mathematical, we can write above expression as the instantaneous acceleration of an object at a given instant is the limiting value of the average acceleration as the time interval approaches zero. This describes how fast the velocity is changing at a specific moment in time. The previously discussed classification of motion can be stated as follows: an object is either at rest or in motion. If it is in motion, it can be categorized as either uniform motion or non-uniform motion. Furthermore, if the object is in non-uniform motion, it can be further classified into uniformly accelerated motion and non-uniformly accelerated motion. In this video, we explored key terms in kinematics, including scalars, vectors, distance, displacement, speed, velocity, and acceleration. Understanding these concepts is important as they form the foundation for analyzing motion in physics. In our next video, we'll dive deeper into motion in a straight line, where we'll apply these concepts to understand how objects move along a single direction. If you found this video helpful, don't forget to like, share, and subscribe to the channel for more physics lessons. Also, press the bell icon to get notified about future updates. Stay tuned and see you in the next video.